All right, so I have started the new year's worth of lectures, and like the last lecture we did, the iPad notes are here, and so far I'm feeling energetic, so the actual video of the lecture is here.
I am going to be...
Yeah, okay, well, there it is. And hopefully I'll continue to do that. So the videos, because of space limitations, are going up on YouTube. And you can probably just, like what I just did, I just searched on EE208 _ L1. And just do a search on that and you'll get to the videos. I think what I'll do is in iLearn, like here, I'll include a link to where the video is. That's the easiest thing. Okay, so that's that. So let's see where we were last time. Oh, good. Okay. So I just want to see where we ended up last time. Oh, so we started doing this review of the formalism, Braun-Ket notation, introduce the inner product, concept of basis vectors, which will become our basis functions, and just so you have something physical to think about, since we're doing crystals, which is a periodic collection of atoms, our basis functions will be, you can think of them quite happily as atomic orbitals, so like s orbitals, p orbitals. That's as far as we'll go, but d orbitals in general. For those would be the basis functions in which we're going to be working. And so all these is, when I start, I guess that's as far as we got. So I guess we'll just continue on from here. So we showed that we could, once here we're just working in a 3D vector space, and formally the concepts are identical, and this is what you already know. You can write any vector as just a linear combination of x hat, y hat, and z hat, something you've been doing for a long time, and this is, if you wanted to write down a compact expression for it, the weights for each x hat would be the dot product of your vector with that x hat. And then in our new notation over in the red, I simply rewrote it using our Braun-Ket notation. And then when you look at that, you have v on the left, and you have a v on the right, and so that thing must be the identity operator. You hit any vector with that, and you get back the vector. We're going to be working with an orthonormal basis. Ortho means it's orthogonal, right? Just like your x hat, y hat, and z hat, you take the dot product and you get 0 between any one of them, unless it's the same, and then you get 1. So that's the normal part. So they're orthogonal and normalized. And we're always going to be using this Ket notation, so there'll be some collection of, and you can think of them as these localized atomic orbitals. So some collection of localized atomic orbitals. For the most part, if, say we think of that as the s orbital on each atom, then I would be the index for the atom in the crystal. So like, if you have a crystal, the I would be the index of each atom in the crystal. And if you just had one orbital, like an s orbital, then I would just be each s orbital on each atom of the crystal. This is for all I, an element of however many, say, atoms you have. Orthonormal just means that you take the dot product or inner product between any two of these guys, and you get, for some discrete set of orbitals, you just get a Kronecker delta function. You all familiar with the Kronecker delta function? So if I equals j, it's 1, and if I is not equal to j, it's 0. Right? That's your Kronecker delta function. And this basis is complete, which simply means that if we do this, sum I, ui, that is indeed our identity operator. You hit any vector in this space with this thing and you get the vector back. It just means you can represent any vector with a linear combination of these orbitals. You can represent any vector in this space as a linear combination of these orbitals. So they're complete. Orthonormal and complete. Sort of introduce this in terms of the vectors in 3D space that you know and love for a long time. But all this formalism and machinery is identical if we think of these things instead of like x hat, y hat, and z hat as these functions in some function space. And we already gave examples like your sine functions for a particle in a box, your plane waves. You can represent any well-behaved function as some linear combination of plane waves, and you call that a Fourier transform, right? So as long as your function is well-behaved, kind of goes to 0 and infinity and things like that, you can represent it as this linear combination of plane waves. And just to sort of formally show how we go from here to our function space, we need to talk about the R representation. So one complete continuous basis is what they call the R representation. And it sounds very fancy, but it's actually just what you've been doing all your life. So if we have some state, say our s orbital on an atom, your s orbital is just like or just a spherically decaying exponential function. The way I've written that ket there is just it's sort of abstract. It's this s orbital, but not in any particular representation. I could represent this s orbital as its Fourier components. That's one way to represent it. I could represent it as the usual way you represent it in real space. And the way you represent it in real space in this notation is to do this. You hit it on the left with this position operator, and that is, by definition, it just gives you what you've always called your function phi as a function of position, your normal function. So until I hit this on the left with something, it's just sort of this abstract function. You could write it in any representation, some linear combination of other functions, for example. But when you hit it on the left with R, it's just your normal function that you know and love. Some function as a function of position. Another way to think about this is that when I hit it with R, all I'm doing is at that point in space, represented by R, this gives me the value of that function at that point in space. So R is some point. I hit this abstract function with R, and it just gives me whatever value it is at that point in space, that's really all a function is. For these continuous R is a continuous basis. The normalization is a little different. It's a Dirac delta function. Instead of a Kronecker delta function, it's a Dirac delta function. Are you all familiar with a Dirac delta function? Or if you integrate this guy over all space, d cubed r prime delta r minus r prime. It's just 1. Basically, a Dirac delta function is, you can think of it as like an infinitely high spike, right when r equals r prime and 0 everywhere else, but it's normalized in such a way that when you integrate it, it's infinitely thin, infinitely high, but the area under the curve is always 1. And so the identity operator is, this is really what we use. And it's sort of just implied in everything we do. D cubed R. So when you have a continuous basis like this, and a dot product implies an integration. Your sum becomes an integral, that's all. Your sum becomes an integral because it's continuous instead of discrete. So before we had a sum over all I. That sum over all I is replaced by an integral over all R, because R is continuous. And so that allows us to evaluate this inner product that I've just been writing down a little bit. Evaluate just a little bit in an ad hoc way. So if these are two states, psi and phi, and these states would be, say, atomic orbitals or some eigenstates of your Hamiltonian, but right now I've just written them down as some two states without a basis. These, you can think of them as, if you like, two different eigenstates of your Hamiltonian, which are functions. So the way you actually sort of formally go from this, which is abstract, to something you actually can calculate, you insert, and this is what we are going to be doing a lot, you insert the identity operator. I can always insert an identity operator. So this, along with the integral, we just said is the identity operator. Oh, this is equal to I, sorry, my identity operator. So we can always insert, right? An identity doesn't do anything. But this is just a definition of what I mean, this is what you would always just write down in the first place. This is phi of R. And this, since we flip the order of psi and R, is just the complex conjugate. So this is psi star of R. And this is what you learn in, like, first semester quantum mechanics. You take the inner product of two wave functions, you complex conjugate one, and you don't the other, and you integrate. So it's just a lot of formal machinery to get back to something you've been doing for some time. Right? So this shows you how to get back to, if I wanted to take the inner product of two wave functions, you end up with what you would have been doing from a long time. So it just becomes psi star phi, and you integrate. And what we're really going to use is the matrix elements of the Hamiltonian, or in general, the matrix elements of an operator. We'll mostly just be doing the Hamiltonian. So we will want to evaluate matrix elements of the Hamiltonian. And formally, we do that by inserting an identity, one of our identity operators here and there. And so you have two integrals, integral d cubed r, integral d cubed r prime. And for all the Hamiltonians we're going to be working with, this just gives me h of r delta r minus r prime. And this is what we just had before. This will be phi of r prime. This, because I flipped it around, will be psi star of r. I got my two integrals, so I can do immediately the integral over r prime because I have my delta function here, which just turns r prime into r. So doing the integral over r prime, just convert wherever I have an r prime, I replace it with r, and so I end up with exactly what you would have written down after any quantum mechanics course. Psi of r, h of r, phi of r. And this is the matrix element of the Hamiltonian. And we're going to be doing this because this is how we're going to be converting Schrodinger's equation the way you're used to seeing it in terms of some, grad squared and potential into something that looks like a matrix that we can stick into MATLAB. So now let's do an example. to make this real and start looking at atoms and what happens when you bring two atoms close enough so that they can feel each other and start to interact. So the idea is we'll start with two atoms, and then we'll go from two atoms to an infinite line of atoms periodically placed, and that'll be our first crystal, a 1D crystal. And we'll calculate the eigenstates of that and create our first band structure. So we'll start with two atoms first. So let's just keep it real simple and think of two hydrogen atoms. And initially they're far apart, and we're going to bring them close together, bring them close enough together so that they can, their wave functions start to overlap. And our basis, this basis we've been talking about, is going to consist of exactly two states, an s atom on one hydrogen atom, an s orbital on one hydrogen atom and the s orbital on the other hydrogen atom. So our basis consists of two s states. So pictorially, we've got hydrogen atom number 1 here, hydrogen atom number 2 over here, and s orbital is just a spherical, nice spherical wave function that exponentially decays away from the origin. Okay, and so this will be centered at position R1, this is centered at position R2, and our two basis states are just going to be S1 and S2. Those are our two basis states, which we're going to use to represent our wave function, the s orbital on each hydrogen atom. And each hydrogen, the proton has some in terms of, as far as the electron is concerned, each proton has some attractive potential, your Coulomb potential, which is just your, so this would be the potential over here on atom 1, and the potential on the other atom is the same, except we just replace R1 with R2. Okay, so those are that's the potential due to the proton. The potential that the electron feels due to the proton of each hydrogen atom. Right? A hydrogen atom is just a single proton. So each electron feels that potential due to the proton. Okay? And there's only going to be, let's just think of having one electron in this problem and two states, so we don't have electron-electron interactions to worry about. Okay, so this is it. We have our potential, right? Schrodinger's equation, we just have the kinetic term, p squared over 2m plus the potential, and we just wrote down what our potential is. So our full Hamiltonian, H, is just p squared over 2m plus the potential due to proton 1 plus the potential due to proton 2. And these s orbitals are eigenstates of their so initially we take our hydrogen atoms to be infinitely far away, and so these s orbitals will be the eigenstates of the individual atom that they sit on. Okay, so that means that p squared over 2m plus u1 of r acting on s1 is just the energy, I don't know if I'll call it that. Just the energy of that s orbital times s1. I mean, right, that's Schrodinger's equation. That's just telling you that that s orbital is an eigenstate of the Hamiltonian, the eigenstate of atom, of the hydrogen atom number 1. Right? That s orbital is the eigenstate. I mean, that's what the definition of an s orbital is, right? They're the eigenstates of the atom. So this s orbital is the eigenstate of hydrogen atom number 1, and the other s orbital is the eigenstate of hydrogen atom number 2. And the energies are the same because the s orbitals in every hydrogen atom is identical, right? So they have the same eigenenergy. And now let's think about bringing them close enough together so that these two wave functions start to overlap, and the s orbital on atom 1 starts to feel the potential of atom 2 and vice versa. So what happens as you bring these atoms closer together? To understand that, we have to start taking we're going to take the matrix elements of the Hamiltonian, and we're going to create a 2x2 matrix. So we're going to bring these guys, start bringing them closer together, not exactly together, but closer together. And then we're going to take the matrix elements of H. And there's only 2 orbitals, so we're going to get like, the matrix elements will be like 1, 1, 1, 2, 2, 1, and 2, 2. So you're going to get a 2x2 matrix, which is a representation of your Hamiltonian. It's called your Hamiltonian matrix. So let's go ahead and construct that, and then the eigenvalues of that matrix will be your new eigenenergies as I bring these 2 atoms together. Okay? And this is sort of the beginning of a procedure that we're going to be doing a lot. This is the way the game always works. You figure out the matrix elements of your Hamiltonian, you put it into an n by n matrix, you send it off to MATLAB, and you get your eigenvalues and eigenvectors. And that's the way the game is played. It gets more complicated, but that's a real fundamental procedure at the bottom of everything. Okay, so let's go ahead and construct the matrix elements of the full Hamiltonian. So the full Hamiltonian is at p squared over 2m plus u1 plus u2. The potential, both the potentials, okay? And so this is going to equal, well, before I do that, okay, yeah, we're good. Okay, so that's going to equal, maybe I should write it out. So that's S1 p squared over 2m plus u1 plus u2 S1. So that's what we're talking about. All right, that's our Hamiltonian. And we know that this part, acting on S1, just gives me that epsilon 0 S1, because it's an eigenstate of that part of the Hamiltonian. So I can just replace this by epsilon 0, since when that hits S1, it just gives me back epsilon 0 S1. So that's equal to epsilon 0 plus U2. Oh, I forgot the, I'm sorry, this is maybe easier for me than for you. Let me just, instead of right away taking the matrix element, just look at what the Hamiltonian does when it hits S1. Sorry, I hope you have erasers. It's real easy for me. So we just want to understand what happens when this full Hamiltonian hits S1 before we go ahead and take the matrix element. And so this is what you get. And for let's do the same thing for S2. Again, the full Hamiltonian, p squared over 2m. Let me just reverse the order of u1 and u2 plus u2 plus u1 hitting S2. Again, that's just going to, the first 2 terms are just going to give me epsilon 0 again, because S2 is an eigenstate of those 2 terms. So I again get epsilon 0 plus u1. Okay, and so now we can go ahead and calculate using these 2 things we've just written down. Go ahead and actually calculate matrix elements. So we always start off with the easier ones, and the easy ones are always what they call the diagonal matrix elements. So that'll be like S1, S1. So S1, H, S1, well, to evaluate that, I just go over here and put in, hit it on the left with S1 here. We've already done sort of the right-hand side. And that's just going to give me, epsilon 0. Oh, I'll write out all the terms the first time. S1, S1, right? Epsilon 0 is just a number. It's a constant. So, I can pull it outside of that matrix element. Remember, the matrix element is really an integration over space, right? This part of the matrix element is our integral. D cubed R, I can pull this is just in energy. It doesn't enter into an integral over space of my phi S1 star R phi S1 of R. And since, we're using an orthonormal basis, by definition, this is just 1, right? That's just 1. Plus the other term, S1, U2, S1. And so this other term is just going to give me some, the orbital S1 starts to feel some potential due to U2. It's negative, so it wants to pull, if I do this integral, these functions are positive definite. The S orbital is always greater than 0. U, if we go back and look at that potential, is always negative. Right? These are my potentials, U1 and U2. They're always negative. So that integral will just give me some negative number. It'll mean a slight downshift of the energy because I'm feeling some negative potential somewhere else. So it's just going to give me some correction to epsilon 0. We're just going to define that as some delta, some shift, which would be negative. I really don't care. And so we're going to define this eventually as just some new energy. So this would be like epsilon 0 plus some shift, and we're just going to call that some slightly renormalized energy because I'm feeling this other potential nearby. The energy of that s orbital would get shifted down a little bit. Make sense? If you feel a negative potential nearby, you'll shift the energy down a little bit. So this is our first diagonal, 1 of 4 here. This is our first, and this is what we call H11, the 1-1 element of our matrix H that we're constructing. Right? There's going to be 4 elements, 1, 1, 1, 2, 2, 1, and 2, 2. You're going to get a 2 by 2 matrix. And so this is our H11. It's just the original s orbital energy plus some slight downward shift. Okay, well we can do the other diagonal one. S2, H, S2. Again, you're going to get the original s orbital energy plus S2, U1, S2. This will be that same downward shift. It's just these orbitals are identical. They're just one is on atom 1, one's on atom 2. So this one on s orbital on atom 2 is feeling the negative potential on atom 1. That potential looks identical to the potential on atom 2. So this is the same shift, delta, which is negative. And so that's also just epsilon 0 plus some slight shift from the original. So H22 is also equal to this some slightly shifted energy from the original. So that's kind of trivial so far. Now the important stuff are the off-diagonal matrix elements. That's where something sort of qualitatively different, why the system changes qualitatively from the initial system. So we need to look at S1, H, S2. And if I let H act on S2, one part of it gives me back epsilon, the s orbital energy. And now I'm left with this thing. Just to save on notation, instead of writing S1 and S2 every time, let me just start referring to them as 1 and 2 in the kets and bras. Those are my states, S1 and S2. I just call them 1 and 2. So that's the overlap integral between orbital S1 and orbital S2. And since we sort of by proclamation said these orbitals are orthonormal, that's going to be 0 for us. In reality, 2 s orbitals shifted in position are not orthonormal. And so there is this, so the people who are doing quantum chemistry, I don't know if anyone's like chemistry, in all the quantum chemistry codes like Gaussian, they have to take into account this overlap matrix because they really do use things that look like atomic orbitals as the basis. They're simulating molecules, and you have to keep track of these because the basis really is not orthonormal. But for most of what we do, we're just going to assume it's orthonormal and ignore what you call this overlap matrix. Okay, plus the other term, plus 1, U1, 2. And if I let, and this is just to make things look pretty, if I let H act on, in this case, what I did was evaluate this first and then hit it on the left with S1. If I now evaluate this first, right, H acting on S1 gave me so H acting, this guy, we're looking at this up here, and I've just taken, because I flipped it around, it's sort of the Hermitian conjugate of all that. But since everything is real, in this case the s orbitals are real, U is real, epsilon is real, it really doesn't matter. So I can let H act on S1 first, and then let it hit S2. And in that case, you get, well, this term is the same, epsilon 0, 1, 2, plus 1. And so instead of U1, the only difference is you get a U2 over here. U2, 2. All right, these two things are the same. They're equal. And so just to make things look pretty and symmetric, I'm going to add them together and divide by 2 to get the final form of my matrix element. So finally, for my off-diagonal matrix element, S1, H, S2 is equal to epsilon 0, 1, 2 plus 1 times U1 plus U2 over 2. And this is just to make it look pretty and symmetric. And I would go through the same procedure, and I get what, for the other off-diagonal matrix element, I get exactly the same thing. This order is switched, but I'm going to set this term to 0 in a minute anyway. And in this case, all S1 and S2 are real. These things are the same. Otherwise, they'd be complex conjugates of each other, which they must be, because we all know that a Hamiltonian is Hermitian. And so when you turn this Hamiltonian into a matrix, like what we're doing, the matrix itself must be Hermitian. So when you go ahead and calculate, once you really trust yourself, you only need to calculate like the upper half of the matrix elements, because the lower half have got to be the Hermitian conjugate of the upper half, right? In any Hamiltonian matrix. I mean, it's good to check if you don't fully believe your calculation, to calculate those lower half elements and make sure they really are the Hermitian conjugate of the upper half. But people get lazy. I only calculate the upper half mostly. Fill in the lower half, because it has to be the complex Hermitian conjugate of the upper half of the matrix. So we've calculated all 4. I think for now, just because we're never going to do anything with the overlap matrix, let's just get rid of it right now. So because we've assumed our basis set is orthonormal, those terms are 0. And orthonormal basis, remember, you get a Kronecker delta unless it's 1 if the states are the same, and 0 otherwise, right? And so we can now write down our Hamiltonian matrix, our 2x2 Hamiltonian matrix. So H, we've taken this and turn it into an actual matrix that you can stick into MATLAB. So you have epsilon 0 tilde. You have these off-diagonal terms, 1, Okay, 1, u1 plus u2 over 2, 2. And the same term down here, 1. Let me call that u bar so I don't have to keep writing it. 2 and epsilon 0 tilde, where u bar is just that u1 plus u2 over 2. By going through this exercise in a real crystal, you get all the symmetries of your matrix elements right, you get the signs right. The magnitudes, because we're going to be using empirical models, the magnitudes are really just parameters that people have figured out to give you the correct band structure. So these off-diagonal matrix elements become a parameter, and the parameter we're going to call them is, what are we going to call them? T. So finally, our Hamiltonian matrix for the two atoms as you bring them close together is just E0 tilde T, T, E0 tilde. In general, these would be complex conjugates of each other. That would be the form of your 2x2 Hamiltonian that you've constructed. And in this case, and actually in when we do real crystals, the potential is negative, so, and for the s orbitals, the orbitals are positive. So this this integral, this is just an integral of phi1 star, phi2 times the potential. Phi1 and phi2 are positive, the potential is negative. So these t's are actually a negative number, something less than 0 for the s orbitals. Okay, so we have brought this down to, and this is going to, basically a very simple form of a tight binding model. And tight binding models are how we're going to start and spend the first number of weeks of the course working with. Okay, so we've got this Hamiltonian. Now what? Well, I guess you want to know what the new eigenenergies are of the system as you bring your atoms close together, so you solve the eigenvalue problem. Right, just to remind you, the eigenvalue problem is, H psi equals E psi, and the only way that happens is if the determinant of H minus E times the identity, that's right, determinant equals 0. Right. H psi equals E psi is your eigenvalue problem. And so that means that H minus E is just a number times the identity matrix acting on psi is 0. And the only way for a non-zero psi for that to be true is if the determinant of H minus EI is 0. So you solve that eigenvalue problem. For E is just a number. And since it's 2x2, and you don't have any degeneracies, you're going to get two numbers. Because if we go back to our matrix now, so I do H minus E, it means I'm looking at, let me just ignore the tildes from now on, epsilon 0 minus E, T, and in this case the T's are real. Oh, I guess I can keep them. Okay, I'll keep them for now. T star, epsilon 0 minus E. And so that just means that I have epsilon 0 minus E quantity squared minus the magnitude of T squared is 0. So E, my eigenenergies are E equals, what do they equal? E equals plus or minus, it equals E0, my original energy of the system, plus or minus T. Right? These are the two new eigenenergies of the system. And okay, we can keep our tilde here if you really want, a little bit of some shift. But the important thing is not the tilde. The important thing is that plus or minus T. That's what, because before So far, before we brought the, initially, when you think, so if my two atoms are far apart, I've just got, my solution is just going to be, two different atoms with the same energy. The energies are degenerate. And then as I bring them together, I'm going to get an energy spectrum that looks like this, where I have the E0 plus T and the E0 minus T. So I start off with the degenerate system where the energies are the same. As I bring them together, they couple, they split, and the system is no longer degenerate. And if I have one electron, the one electron is going to go into the lowest energy state. This will become filled. The other will be empty. And now, if you think of a molecule, I have my HOMO level and my LUMO level. I don't know if you know anything about molecules. This would become your HOMO. Anyone know what that stands for? Other than you? Do you know? What is it?
The same.
HOMO is the highest occupied molecular orbital. And LUMO, so this would be, we've brought two atoms together. We've made a chemical bond. So the atomic energies coupled, they split apart. And if they're like sharing one electron between them, the electron will go to the lowest state. That lowest state becomes your bonding orbital, or what the chemists call your HOMO orbital, your highest occupied molecular orbital. Highest occupied molecular orbital. And the LUMO is the lowest unoccupied molecular orbital. The HOMO and the LUMO, the lowest unoccupied molecular orbital. So those are the eigenenergies. Now we can look at the eigenvectors, the wave functions.
Is that HOMO is for binding energy or for anti-binding energy?
HOMO will be the bonding state.
For the binding energy or binding state or anti-binding state?
It's a binding state. People usually call it bonding state. Yeah, the orbitals are bonding, and the LUMO is anti. I'll draw it. Well, let me calculate the eigenvectors, and then you'll see that one is symmetric and one is anti-symmetric. The symmetric one is your bonding state, the lower one. Your anti-symmetric one is the anti-bonding state, the LUMO. But it comes right out when you look at the eigenvectors. So let's do that now. So those are the energies. Now let's look at so did I actually label these? So these are the eigenenergies of the system. And now let's look at the eigenstates, which are your wave functions. So once you've calculated the eigenenergies, the way you get the eigenstates is you go back and you put in the eigenenergy back into here, and then you solve for psi. You solve for this column vector that gives you the amplitude for your wave function. So my wave function psi is a linear, right? My basis, it's got to be a linear combination of my basis states. Okay, so as I said, we know what E is. We have two E's. I'll call it E plus and minus, and our two solutions. And so you just go ahead and you for each one you put in that E up here, and then you solve your matrix vector problem. So let's go ahead and do that. Let's do it. So the first one I'll solve for is the say E minus, the bonding state. So I'm going to solve for the lower energy. So I put in that E into my matrix. So what's my matrix was, do I have it over here? Let me copy and paste it. There's my matrix over there. So I put in the E minus wherever I have an E. So the epsilon zeros are going to cancel out. And all I am left with is a magnitude of T here. Magnitude of this, the off-diagonal terms don't change. I'll call my C1 and C2 I'll just call them C1 and C2. Okay, so that's how you solve for the eigenvectors. And by definition, this matrix is singular. Its determinant is 0, which means each row it's only 2 by 2. So one row is just a linear combination of the other. So there's only 1 degree of freedom here, and I've got 2 variables. So there's a number of ways to do that. I only need to look at one row. And say if I look at row 1, the equation I get is C1 times the magnitude of t plus C2t equals 0. And I can immediately write down something. I can let C1 equal to the magnitude of t and C2 equal to negative t star. Then I got t squared minus t squared equals 0. So that'll work. Okay, and so then I'll have a wave function solution. What do I want to call this guy? I'll call it H for the HOMO. That'd be my highest occupied molecular orbital. Phi H would be magnitude of t times S1 minus t star S2 all over root 2 magnitude of t, because it has to be normalized. And now remember that RT is less than 0. And also t is a real number for us. So for real t a real number, our bonding orbital, our lowest orbital, is just equal to S1 plus S2 over root 2. So this is the bonding orbital for the lower energy, for E minus equal to epsilon 0 minus t. And if you notice, it's symmetric. So it's symmetric. It is what you were calling the bonding. You were calling binding. I usually call it the bonding orbital. And this also would be the ground state. Now we go through the same thing for the higher energy, E plus, which is equal to epsilon 0 plus magnitude of t. And we put that back into our matrix, H minus E, and now we get minus t. And since our t's are real, I won't bother with the star here. And you solve that, and you get that for C1 and C2, phi of the LUMO, the higher one, is just the anti-symmetric combination, which means, C1 is 1 and C2 is negative 1. So, I mean, if I put in, since the t's are real, negative magnitude of t is equal to t because t is negative. Negative magnitude of t equals t because t is negative. So the solution for C1 and C2 is just 1 and negative 1. Okay? And so I get the anti-symmetric or anti-bonding wave function for the higher one. So for our HOMO, we had the symmetric. So now if we go back to something pictorial, I have hydrogen 1, hydrogen 2. I have these s orbitals that are around them. And so for the bonding one, right, we added them together. And so if you add them together, you get some molecular orbital that looks like this, some kind of picture you've probably seen before. And so this is, the proton of hydrogen 1 and hydrogen 2. And the other one, so this is for phi H, our HOMO orbital, which is 1 plus 2 over root 2. And the anti-symmetric one, I subtract one from the other, and so if you subtract one from another, you'll get a 0 right in between. So you'll get a null right in between. And this is your anti-bonding one, your anti-symmetric orbital. Right? Your bonding and anti-bonding. When you look at the wave functions, it's clear that the upper one would be bonding. The wave clouds are all overlapping. It goes, it's holding the two protons together, and the other one has a null in between, a 0, an exact 0 in between. This is your anti-bonding orbital, your upper one. And this is a very, very general result, that the bonding orbital, the lower orbital, will be the symmetric one, and the anti-bonding, the upper one, will be the anti-symmetric orbital with a null in between. And these are eigenstates of a Hermitian Hamiltonian. So one thing you learned somewhere is that the eigenstates, non-degenerate eigenstates of a Hermitian matrix better be orthogonal. And since we've normalized these are orthonormal. So if we do this, we just get, you go ahead and you get, 1, 1. What do we get? Yeah, minus 2, 2. Minus, I don't know how I'm doing this, 2, and plus, I don't know which one I'm flipping. I guess I'll flip the up phi h, so minus 1, 2, plus 2, 1. But these, in our orthonormal basis, these are 0. And so this is just 1 minus 1 equals 0. So these are indeed orthonormal wave functions, as they must be, because they're eigenstates of a Hermitian matrix. And if we go back, if we go back to the two eigenvectors that these came from were, 1, 1, and the other one was 1, negative 1, and they're clearly orthonormal. This was for our bonding energy, and this was for our anti-bonding energy. The two eigenvectors we got from this. And what I skipped, unfortunately, so this is, we got a few minutes left, good, just enough, was sort of the formal procedure. So I went ahead, I calculated all these matrix elements of the Hamiltonian in this basis, and that's all good. But I kind of skipped the crucial step of, how all this, I kind of skipped the lead-in step, I'm sorry, so let's back up. And if you have your Schrodinger's equation that, you first saw in some introductory course, how do you formally turn it into this matrix equation that we were just looking at? So we start off, so this is sort of the crucial page. I skipped, my bad, sorry. So we have Schrodinger's equation, the one that you know and love, just a differential equation, first order, IH bar, ddt psi is H psi. Your H will have your, grad squared term in it and your potential. So you've got this differential equation in both time and space. And we want to turn this into a matrix equation to get this 2 by 2 matrix. And so you have a set of basis functions. You have your known basis functions, your u sub I. And so you're going to be, and since it's a complete orthonormal set, you can form the identity operator. You can write your wave function as a linear combination of these guys. And so the first thing we do is we just stick in a identity operator, IH bar ddt psi is equal to H. Well, let me sum over I, H, and then my identity operator, UI, psi. I'm just stuck in an identity operator. And again, the UI are these known like atomic orbitals. We know what they are. And then I hit the whole equation on the left with uj. So I have I h bar d dt uj psi is equal to sum I uj h ui psi. And this is exactly what we just said was our Hamiltonian matrix element, H, I, J, right? That's exactly the way what we called our Hamiltonian matrix element. And this, if we write our psi as a linear combination of the UIs, this is just the CI for that linear combination. So psi is just sum I, CI, UI. And this is that weight, C sub I. And this is simply C sub j of that weight, some complex number. Right? We write our psi as a linear combination of the basis functions. There's a complex number. And so now I've converted this differential equation in space into a matrix equation of the form IH bar ddt Cj, which would be a function of time, is equal to the matrix H sum I. Sorry, this is HJI, not HIJ. Sum I, H, JI, C sub I. Let me correct that. This is HJI. Indices are important. And if I write that out in sort of using a real matrix, IH bar ddt C1, C2 to Cn would equal my n by n Hamiltonian matrix H. These are all the n by n matrix elements acting on C1, C2 dot Cn. And now I have this matrix equation that I can stick into MATLAB. We aren't worried about, but this is a procedure of how you convert this differential equation that you've always dealt with into a matrix vector equation. You choose a basis set, you take the matrix elements, you create this n by n matrix for your Hamiltonian. And we aren't worried about time dependence. All we're going to focus on is this right-hand part of the equation, HCN, and we're going to be worrying about calculating the eigenvectors. So we're going to take this right-hand side and worry about this problem, which is what we just did for the 2x2 case. We just went through that procedure for the 2x2 case. So the procedure is, if you have a Hamiltonian, you calculate the matrix elements, you form your n by n matrix, and you calculate the eigenvalues and eigenvectors. And that gives you a lot of what you need to know. I guess it's time again. Okay, a couple of announcements. Discussion is canceled for tomorrow, or Friday. No discussion on Friday. There is homework 1 is already up there. You can look at it. I went through enough to maybe do one of the problems. I'll formally assign it next Monday. we can discuss Friday. It'll be due to the Monday after that. Anyone can enroll who wants to enroll. I talked to our graduate person, and I think the discussion section was changed to this room, so there's plenty of room. And I guess that's it. Okay. See you Monday.